Welcome to MDU. To understand the extreme physics of a dying star, we have to look closely at millions of high-tech hydrodynamic simulations. Our baseline tests cover a massive range: stellar masses from 1 to 1,000 times the size of our Sun, crushing densities hitting 10 to the 18th kilograms per cubic meter, and timeframes spanning fractions of a microsecond to millions of seconds. These are helium stars. They are born in the extreme conditions of the early universe through a process called a core helium flash, a violent ignition deep inside a massive star that burns away its hydrogen envelope and leaves behind a volatile, helium-rich core. With a standard hydrogen-rich star, we can usually plot its life cycle and death with near mathematical certainty, but stripped-down helium stars play by different rules. Their final moments completely defy simple prediction. Running these masses through stellar evolution and hydrodynamics codes like MESA and FLASH, we see them face one of two opposite outcomes. They either detonate outward into a brilliant supernova, or they go completely silent, succumbing to a direct collapse into a black hole. So what exactly tips the scale? Why does one star burst outward to seed the cosmos, while another is instantly erased into a dark void? To solve this paradox, we have to analyze the data linearly. By tracing the entire mass spectrum from the smallest stars up to the absolute largest, we can pinpoint exactly where the physical rules of stellar death flip. This horizontal data scale tracks stellar mass, and we are starting at the lower end, the bracket between 1 and 50 solar masses. You might expect a smaller star to go out with a standard bang, but the data here reveals a 100% rate of direct collapse. Gravity wins instantly. There is no explosion, just a sudden black hole. But as we slide right on the scale into the chaotic middle, ranging from 50 to 150 solar masses, the data totally fractures. Here, the physics completely invert. 90% of the stars successfully ignite as violent supernovae, and just as quickly as that trend appears, it breaks. Move slightly higher into the 150 to 300 mass range, and the outcome abruptly reverts to a 95% direct collapse rate. This whiplash in the data is driven by intense external forces. One variable is high metallicity, an abundance of heavy elements in the star's environment, that increases internal helium shell burning. That burning creates strong outward pressure, actively fighting against the star's gravitational collapse. Another major factor is close binarity. If a helium star is locked in a tight orbit with a companion star, that neighbor will aggressively siphon away its mass, constantly altering the physics of its final collapse. For these intermediate mass stars, death is an ongoing tug of war. The final outcome isn't guaranteed. It is decided by the delicate balance between the star's crushing internal gravity and its immediate external environment. But external factors alone cannot explain this massive volatility. We have to look inside the star to find the specific hydrodynamic engine driving these rapid shifts in survival rates. The answer lies in multidimensional vortex formation. The extreme convection heat, rapid rotation, and twisting magnetic fields spin up violent storms deep within the star. These internal vortexes act like giant centrifuges. They accelerate the star's mass loss to the outside, rapidly stripping away its outer layers while completely altering the density of its burning core. By changing how much mass sits at the core versus the outer layers, these vortex-driven storms dictate exactly how much energy a supernova needs to successfully shatter the star and break out into open space. As we extend this scale to its absolute upper limits, we leave the chaotic middle behind and enter the realm of the cosmic behemoths, the 300 to 1,000 solar mass range. Up here, fluid chaos is overwhelmed by physical limits. Once a star passes 750 solar masses, reaches a core temperature over 1 billion degrees Kelvin, and hits a density exceeding 10 to the 18th kilograms per cubic meter, uncertainty vanishes. Under these strict singularity thresholds, the outcome is uncompromising. We see a 100% rate of direct collapse into an intermediate mass black hole. The gravity becomes so intense that no outward explosive force can ever escape it. The middle of the mass spectrum may be a chaotic puzzle of fluid dynamics and binary orbits, but the extreme upper limits leave absolutely no room for chance. Collapse is a certainty. We've seen the internal mechanics, But how do these thresholds impact the broader cosmos? In the early universe, massive helium stars operated as primary thermal engines. Their intense life cycles dictated exactly where and when younger stars were able to form. For those stars in the chaotic middle mass range that successfully detonated, their violent supernovae ejected specific arrays of heavy elements. Those distributions directly mapped the chemical evolution and structure of modern galaxies. And the silent direct collapses are just as valuable to astrophysicists today. Because we know the exact mass brackets that vanish without an explosion, we know exactly where to look for sudden ripples in spacetime, giving us precise targets for gravitational wave astronomy. A helium star's death is never a random roll of the dice. It is a strict, predetermined cosmic equation, balanced entirely by its mass, its environmental metallicity, and the fluid vortexes churning inside its core. Make sure to like this video and subscribe to the channel for more deep dives into space.